Hello everybody and welcome to another ATC Maths and Science tutorial video. Today we'll be dealing with acids and bases and more specifically the pH calculations in the section acids and bases. But before we jump into the calculations, as it is expected in anything to do with physics, we've got to understand a few definitions, a few terms that will make the process of dealing with the pH calculation a lot easier. The first few definitions we're going to come across is firstly the definition of an ampholyte. So as we can see listed on the page, an ampholyte is a substance that can act as either an acid or a base. Typical example of an ampholyte is water. So if you add water to an acid, it will behave as a base. If you add water to a base, it'll act like an acid. And when we say act as an acid or act as a base, we mean that it'll either be a proton donor or a proton acceptor. We also get into some finer details when it comes to the definitions of acids, specifically the three definitions: monoprotic, diprotic, and polyprotic. A monoprotic acid is an acid that donates only one proton because it only has one proton to donate. Classic examples of monoprotic acids would be HCl, HNO3. They only have one proton. Diprotic acid can donate two protons, and polyprotic acids donates many protons. Poly from the Latin words for many. When it comes to any calculation that we have in physics, especially in the section chemistry, I'm sure most chemistry students realize that we need to have some sort of balanced chemical equation to work with things. The balanced chemical equation we can use for a pH calculation is the hydrolysis reactions, which we're going to get into now. But what we must notice the following, that there's a long way of doing a pH calculation, and there's the shorter way of doing it. The shorter way requires us to know these definitions. Acids, they help us or will help us to get to doing our pH calculation in a much quicker manner. But before we go into the quicker way of doing the pH calculation, let's learn the not very much longer but slightly longer method, so that when we finally discuss how to do this in its short form pH calculation, it will be a lot more understandable. That's what we really want to do. We want to understand what we're doing beforehand. So let's get into hydrolysis reactions. This is going to be the balanced chemical equation that to use in order to be able to do pH calculation. So what is a hydrolysis reaction? What does it entail? Hydrolysis means that we're adding water, to put it simply, the addition of water, right, to get into two hectic reactions. So hydrolysis is simply the addition of water. And if we look at the first example here, this is going to be hydrolysis of a monoprotic acid. Now, I deliberately did monoprotic acid and diprotic acid. For those of you who are wondering, yes, they will test something like this in a question paper. Say to you, complete the following hydrolysis equation. So we have to know how to do this anyway. We need to know it just in order to deal with how to do the pH calculation. We also need this in order to be able to answer questions where they ask us for how to complete a hydrolysis equation. So as we can see here, it's okay. So as we can see here, we're dealing with the hydrolysis of a monoprotic acid, and the first example gives us HCl plus H2O. And following the definition of an acid and base according to Bronsted and Laurie, our acid HCl donates its proton to the H2O, and it forms H3O plus. The HCl, having lost its H, will now form Cl minus. You can see it in another example as well. We have got HNO3 plus H2O. HNO3, as we can see, that's our acid. H2O, an ampholyte, will behave as a base. And what happens here? H from the HNO3 is donated to the H2O for it to form H3O plus, and the HNO3, having lost its hydrogen, will become NO3 minus. The base, which has now accepted a proton to form an acid, The product is now known as the conjugate acid. So the base forms after accepting a proton, the conjugate acid. And the acid, after donating a proton, will then be known as the conjugate base. It means, what do we mean when we say conjugate acid, conjugate base? That means that if H3O plus has to be involved in a further reaction, like if you take this H3O plus out of the solution and use it in another reaction, it would act as an acid. And the NO3 minus, if you had to take it out of the solution and use it in another reaction, would act as a base. So conjugate acid, conjugate base. Right? So that was the hydrolysis for a monoprotic acid. Let's do the hydrolysis for a diprotic acid. So as we can see here, diprotic acids, the hydrolysis for it occurs in 2 steps. It has 2 protons, so we expect it to donate its 2 protons not all at once, but 1 step at a time. So as you can see, the steps are listed below, step 1, step 2. So let's use probably one of the most famous diprotic acids to deal with, which is H2SO4. So H2SO4, water is added to it. It donates 1 of its protons, and as you can see, once it's lost 1 of the protons, it's formed HSO4 minus, which would be the conjugate base. Water, having accepted a proton, would now form H3O plus. Now, this conjugate base here, this HSO4 minus, it still has another proton to donate. So we take it down into step 2. But in step 2, it's going to act as an acid, HSO4 minus. It still has a hydrogen to donate. So it donates it to the remaining water that's been added, H2O. And it will now form even more H3O plus and SO4 2 minus, having lost 1 more proton. Now, this interesting behavior of HSO4 minus, you can see in the first step, conjugate base, second step, an acid. It leads to a very famous question about once you write down, or sometimes they give you in an exam paper, the hydrolysis of a diprotic acid. They'll ask you, identify the ampholyte. And what do all of us want to do? We're really quick to write down the ampholyte's water. You know, that's what it is. It's one of the first things we're taught or told about ampholyte. So, the classic example of an ampholyte is water. However, in this reaction, we don't have enough evidence to support the fact that water is an ampholyte. The first reaction, water behaves as a base. In the second step, behaves as a base. Not enough information to prove it's an ampholyte. But if you look at HSO4 minus, in the first step, it is a conjugate base. In the second step, it's behaving as an acid. So if they ask us, identify the ampholyte in the above reaction, ampholyte is HSO4. If you want to know an easy way of identifying ampholytes, other than water, easy way to identify an ampholyte that is not H2O is to look for a substance that has a hydrogen in front and a negative charge. So that means it's a substance that has the ability to donate a proton because it has a hydrogen present, and it has a negative charge, which means being negative, it can accept a proton. Because it's negative, it's easy for it to accept something that is positive. Right? So from here, you can always try, if you want to do the hydrolysis of a triprotic acid in this case. So you know this is going to these steps, right? But so far, we've been focusing only on hydrolysis of acids. What about bases? So we're going to look at 2 classic examples: the hydrolysis of a metal hydroxide, hydrolysis of a base, just any typical base, to a metal hydroxide. The way we write down the hydrolysis reaction is a little bit unique. Say metal hydroxide, it's any base that ends with an OH, NaOH, or OH2, AOH2, right? Sodium hydroxide, barium hydroxide. The reason that it's unique is we're dealing with hydrolysis. So normally we would say here, plus water, this point. But we're not saying plus water. We're putting the water above the arrow. What we do is we split the compound into its two ions. There's a reason behind all of this, that if you had to do it with the plus H2O, you end up with H2O on the left-hand side of the equation and on the right-hand side of the equation. That sort of just complicates matters in terms of how you write it down. It's like you got just this, the reactant and product are, one of the reactants and one of the products are the same. So it's simpler to not stress too much about it. Just like, okay, when I'm doing hydrolysis of a metal hydroxide, just write the H2O above the arrow, take the compound and split it into its ions. Simple, easy way of completing that reaction. From here, we go on to the hydrolysis of a typical base, like NH3, for instance. This, as you can see, proceeds as per usual. Add the water, the base accepts the proton, because this time around water will act as an acid. Accept the proton and it will form OH minus, because that's what we expect. Because as we know, an acid will undergo hydrolysis to form H3O plus, and a base would undergo hydrolysis to form OH minus, as according to the definition of an acid and a base according to us. Now we have all that calculations. Tools we'll be using to deal with pH calculations. So I've just listed equations, the tools that are required to deal with a pH calculation. So pH calculations mean we're going to be using this formula. pH is equal to minus log of the concentration, that's what the square bracket stands for, concentration of H3O plus. We sometimes, not all the time, but sometimes we'll be using the equation listed below. Ka times Kb is equal to Kw. Ka is the concentration of H3O plus, Kb is the concentration of OH minus, and it's equal to Kw, which is a constant, 1 times 10 to the minus 14. When will we know that we have to use this second equation, the one listed here below? Only use this formula when we want to find the pH of a base, just for bases. So examples that we're going to take a look at shortly, they are going to show us firstly an acid, so we'll only be sticking to the use of this first formula. Then later on with a base, so then we'll end up using both these equations to deal with it. So let's begin with the pH of calculations for an acid. Right? So examples in pH calculation. So as you can see, titled here, pH calculations for acids. Let's start off with this first question. So determine the pH of 0.2 mole decimeter HNO3 solution. So let's do this. Right? We're going to be writing down the hydrolysis equation because we need a balanced chemical equation to work with us. So HNO3, write down its hydrolysis equation. HNO3 plus H2O forms H3O plus NO minus. When we compare, as you can see the arrows above, they show us what to compare. We're comparing the concentration of HNO3, the concentration of H3O plus. Why? Because we need the concentration of H3O plus to substitute into this formula in order to find the pH. So, according to our balanced chemical equation, we can see that the ratio is 1:1. Therefore, the concentration of H3O plus is equal to the concentration of HNO3, which is 0.2 moles per decimeter. Taking this concentration, putting it into our pH calculation equation, and this log of 0.2 gives me 0.7 as the pH. It's too bad. Let's do another example. Determine pH of 0.05 mole decimeter HCl. Again, we start off by writing down our hydrolysis equation. HCl plus H2O gives me H3O plus Cl minus. So we've got the whole equation listed down. Again, the ratio shows us the concentration of H3O plus will equal the concentration of HCl because the ratio is 1:1. Therefore, the concentration of H3O plus is going to be the same, 0.05 mole per decimeter cube. That, put it into our equation for the pH. So pH is equal to minus log of the concentration of H3O plus. So it's equal to minus log of 0.05. which is 1.30. It's the pH. But if you notice both examples that we took a look at, and 1, 2, both of them have to do with monoprotic acid. And I deliberately chose these monoprotic acids. The next example we want to look at is going to be for a diaprotic acid. And this one, we're not going to be doing the hydrolysis equations. We're going to use finally that shortcut that I mentioned earlier. Let's look at what we have to deal with this shortcut. Ratio H3O is quicker to use the terms monoprotic, diprotic, etc. So if you're looking at a monoprotic acid, the ratio between acid and H3O plus will be 1:1. So whatever the concentration of the acid is, will be equal to the concentration of H3O plus. Really quick, no reason to write down hydrolysis. If it's diprotic, then the ratio is 1:2. So the concentration of H3O plus will be twice the concentration of the acid. If it was triprotic, then the concentration of H3O plus would be 3 times the concentration of the acid. So let's look at this for this next question and watch how we won't even have to write down the hydrolysis equation. As you can see, the question says determine the pH of 0.06 mole decimeter solution of H2SO4. We know that H2SO4 is diprotic. So the concentration of H3O plus is 2 times the concentration of H2SO4. So if the concentration of H2SO4 is 0.06, then the concentration of H3O plus would be 0.2 per decimeter. And once we have that, we can now perform the pH calculation as per usual. pH is equal to minus log of the concentration of H3O plus, which is equal to minus log of 0.2, which is equal to 0.2. Calculation for this. So in this examples, or set of examples, we know we're going to be dealing the extra step, or the extra equation that we have to deal with. We also don't want to write down hydrolysis reactions here as well. We want to be able to deal with this in a shortcut manner as well. So if we look at a typical base, the most common bases that we get to deal with, they are mainly metal hydroxides. And we're going to use the formula of the compound to determine the ratio. See, if you look at the two examples here, NaOH compared to MgOH2. See, I just put a little marker below the 2. The ratio for NaOH, OH minus to NaOH, the ratio is 1:1. You can see this compound only has one OH in it. Look at the ratio here for OH minus is to the concentration of the base. It's 1:2. It's 2 because there's 2 OHs here. If there's 3 OHs, then you'd multiply it by 3. The concentration of the base, you multiply it by 3 to get the concentration of OH minus. It is a base, so obviously we need to get the concentration of OH minus. So let's take this theory and apply it to an example. So here we say, determine the pH of 0.1 mole decimeter cube AOH2 solution. Concentration of OH minus is twice the concentration of AOH2. You know that from the formula for a compound. So that means its concentration is 0.2 mole per decimeter. But do we need the concentration of OH minus? What we need is the concentration of H3O plus to put it into the formula for the pH calculation. So what do? Use the concentration of OH minus in this equation, the Ka, Kb, Kw equation, in order for us to find the concentration of H3O plus. Concentration of H3O plus times concentration of OH minus is equal to 1 times 10 to the minus 14. We'll replace OH minus, the concentration, with the value we calculated above, which is 0.2. Solve for the concentration of H3O plus. which will turn out to be 5 times 10 to the minus 14, which we can now put into our pH equation and calculate the pH of the base. So pH is equal to minus log of the concentration of H3O plus, which will be minus log of 5 times 10 to the minus 14. We put that into the calculator, and our answer for the pH of